Hello everyone, my name is Xin Li. I am a junior student in AOSS department of University of Michigan. During the summer, I'm working in the SURE program, which is about the planet Mercury. So let me show you what I have done in this 10 weeks work.
First of all, I want to thank two people who helped me so much during my SURE program. The first one is Professor Slevin, the advisor of my SURE program. He taught me knowledge and helped me to develop the research. And the second one is Gina. She is a doctoral student in my department. She is really helpful when I have some questions. She helped me to build up the models and check the results. Without them, I will not have such a wonderful research experience. Okay, let's go back to the research. Here is the outline of my presentation. Firstly, I want to talk about the messenger mission, which is the base of my research program. Secondly, I want to do a brief introduction of Mercury magnetosphere, and it is what I studied during the summer. Then I will go into details about magnetopause to examining the dynamic pressure inside it. And finally, I'd like to talk my model and results. Messenger mission stands for Mercury Surface Space Environment Geochemistry and Region Mission, which is launched on August 3, 2004 by NASA. It is the first spacecraft orbiting the planet Mercury to study its chemical composition, geology, and magnetic field. In my SURE program, I will focus on the magnetic field data. From the picture, we can see a long stick with a magnetometer. That is where our data come from. Then I want to do a brief introduction about the Mercury magnetosphere. As we all know, when a stream of charged particles such as the solar wind interact with the magnetic field of a planet, they will form a magnetosphere, as shown in the picture on the left. Magnetosphere of Mercury has some similarities as other planets. However, here are some special things. The magnetosphere of Mercury is the smallest in the solar system. For this reason, there is no closed draft path for the particles and hence no radiation belts. Here I want to note that from the picture we can see that we feel it's northward inside the magnetopause on the daytime. Using these characteristics, we can identify when the spacecraft goes inside the magnetopause. The aim of my SURE program is to calculate the solar wind pressures inside the magnetopause of the Mercury. In order to achieve that, first, I need to identify the magnetopause crossing to get data at that time, and then I will use SURE models to determine the angle of incidence of the solar wind. After that, we need to correct the angle due to the aberration of the orbit. And finally, using Newtonian approximation to calculate pressure. So for the first step, we try to identify the magnetopause crossing by looking at the plots from messages. Using the characteristics we mentioned before, we can identify the crossing by looking at the z components of magnetosphere. When the spacecraft are crossing the magnetopause, the values of Bz jumps from positive to negative, as shown in the first plot. However, due to the motions of the magnetopause, there may be multiple crossings in a short time, as shown in the second plot. However, we only choose the data when the spacecraft finally goes inside here. We totally choose 156 clear crossings on the dayside during 1 year-and-a-half time, as shown in the plot. Because of the speed of the spacecraft is really fast, we use 30 seconds and 60 seconds to calculate the magnetic field intensity. This blue line shows the magnetopause calculated by the SURE model. From the plot, we can see a good agreement between my dataset with SURE model. Here, we need to talk about the SURE model. It is a well-known model for calculating the distance between the planet and its magnetopause boundary. In these equations, R means the densities between the center of the planet and the boundary of magnetopause. R known and Ks are parameters. Different planet has its own parameters. For Mercury, R known equals 1.45 R Mercury and K equal to 0.5. From the plot on the right side, the different magnetopause is just because we use different parameters. By the SURE models, we can calculate the angle of incidence of the solar wind. Furthermore, since the Mercury is moving 48 km per second, which is comparable to the velocity of solar wind, there is an aberration of the magnetopause, which is about -68 degrees. In the plot, blue line is the ideal position of the magnetopause and the red one is the correct one. Finally, we use Newtonian approximations to calculate the pressures. The equation is shown as follows. Theta is the angle of incidence of the solar wind. We get it from the SURE model, and the K is the Fluent drag coefficient, which is a constant. And for B, it is a measured magnetic field. We calculate by doing a 30-second and 60-second average. From all we did before, we can get what we want, the solar wind pressure. Here is my first result. The left side is the 30-second average of dynamic pressures, and the right side is the 30 seconds. The values of the solar wind pressure is about 7.5 nonpascal. It is reasonable if we compare it with the solar wind pressures on Earth. Here is my second result. We know that the distance of the crossing has a positive correlation with the dynamic pressures to 1 over alpha, where alpha can reflect how the magnetopause reacts with solar wind. The larger the absolute value of the alpha is, the stiffer of the magnetopause. We make the plot for the Mercury and get the alpha, which is larger than Earth. So it shows that the magnetopause of the Mercury is hard to push than the Earth. This is all my work during the SURE program. Thanks for watching.